Hey, we have here another integral today. This one's from MIT Integration Bee 2022, regular season, problem number 4. We have the integral from -2 to 2, absolute value x minus 2 times x minus 1 times x plus 1 times x plus 2 dx. That was a pretty interesting looking problem, and I think we can see that this is going to kind of reduce into a polynomial. I want to simplify all this. I think it's a little hard to deal with like this. So for my first step, I think what I'll do is I'll multiply x minus 2 times x plus 2 and x minus 1, times x plus 1. Let's see what we have. So multiplying x minus 2 times x plus 2, we're going to have x squared minus 4. X minus 1 times x plus 1 is going to give us x squared minus 1, and we'll just have this x here, all still in the absolute value. Now next what I want to do is actually notice that this is an even function. Now the reason this is an even function, if you were to just plug in minus x into this, you'll notice that the square terms is going to just turn, if we plug a minus x in here and square it, we're just going to get back x squared. So the sign will go away here. If we plug a minus x in here, we'll have an extra minus on this thing, but the absolute value will reverse that. So this whole thing is going to be even. And what I can do is use this property of the even function. So we'll use this property over here on the right because we do have the symmetric balance. We're going from -2 to 2. So in this case, f of x is even. What we can do is change this lower bound to 0 and bring a 2 out front. Now the first time that I did this, I had this idea that because now our bounds are all positive, that what's inside here is always going to be positive and we can drop the absolute value. It's actually a mistake. Now yes, x is positive from 0 to 2, but like if you plug a 1 in here, you'll notice that this value is negative. Well, it turns out between 0 and 2, x squared minus 4 is always going to be negative, right? Because 2 squared is 4. So this is always a negative value. But x squared minus 1, it's going to depend where we are. From 0 to 1, okay, from 0 to 1, this is negative. But from 1 to 2, this is going to be positive. So it turns out what I'm going to want to do is break this into two cases, two different integrals. We'll have this region from 0 to 1 and this region from 1 to 2. Now before I fill in this integral here, what I want to do, let's just multiply this whole thing out so we have a single value for what's inside the absolute value. So first, if I multiply x squared minus 1, we're going to have x to the 4th minus 5x squared plus 4. And then now just multiply in an x, and then we're going to have, this is going to be x to the 5th minus 5x cubed plus 4x. So we'll take this value and we'll plug this in for our integral in both cases. Okay, so now that we know what this is, I just need to deal with the sign here and the absolute value. Okay, so we notice in the region between the region from 0 to 1, this is going to be negative and this is going to be negative, but negative times negative is positive. The x is always positive. So we can just, on this first integral here, we're just going to drop the absolute value sign, and this is correct what we have here. On our second integral in the region from 1 to 2, okay, from the region 1 to 2, x squared minus 4 is going to be negative, but now x squared minus 1 is going to be positive. Negative times positive is negative. X again is positive. So this whole thing is going to be negative. So we can drop the absolute value sign in order to have this, but we need to reverse the sign and bring a minus out front. But now we have a really simple integral. We're just looking at power rule. Because we have the same thing here, we'll just integrate it once. So integrating this with the power rule, we're going to have x to the 6 over 6 minus 5 over 4 x to the 4th plus 4x squared over 2. We're going to write that as 2x squared. Just evaluating that from 0 to 1. And then for the second integral, it's going to be exactly the same thing. So I'm just going to copy from here. Okay, next, all we need to do to finish this off, we just need to evaluate it with these bounds, and then we'll be done. Okay, so we'll start by evaluating this at 1. We plug a 1 in here, we're going to have, this is just going to be 1 over 6 minus 5 over 4 plus 2. Then evaluating at 0, notice we have an x in all these, so all this is just going to go to 0. Then we'll bring down this minus 2. Now evaluating at 2, we're going to have, this is going to be 64 over 6. This is going to be minus 5 times 2 to the 4th is 16 over 4. And then plus 2 squared is 4 times 2 is 8. And then evaluating 1 here is going to be exact. Because we have the same integral here and here, it's going to be this thing exactly. So I'll just bring over this over to here. Then we'll just do a little simplification. So this, I'm going to get a common denominator of 12. So we'll write this as 2 over 12 minus 15 over 12 plus 24 over 12. And adding this all together, we're going to have 11 over 12. And so the nice thing, we'll take this 11 over 12, we can use it here and here. Next, we'll do some simplification here. I'll divide my 4 into 16, and we'll have a 4 times 5. So this piece is going to be 20. So to get a value for this, we're going to have, this is going to be 64 over 6. Minus 20 plus 8 is going to be minus 12. If I get a common denominator of 6, okay, so this is actually going to be minus 8 over 6, or minus 4 over 3. So then plugging this back in over here, we have minus 4 over 3. This is going to be minus 11 over 12. I'll use this minus sign to change my sign here. Then multiplying in here, I guess we're going to have, let's see, this is going to be 22 over 12. Multiplying this in, we're going to have 8 over 3. Multiplying this in again, we're going to have 22 over 12. But each of these, 22 over 12, we'll write these as 11 over 6 plus 11 over 6 plus 8 over 3. Adding these together, we're going to have 22 over 6 reduces to 11 over 3. So 11 over 3 plus 8 over 3 will give us our final answer of just 19 over 3. Now, I guess after doing all that, I realized this is actually a more tedious problem than I thought. I think most of the work was just evaluating it. Look at all this here. So, all right, so that's it. Thanks everyone for watching today. Have a good day.